This is 11.2 continued. So last class we were talking about geometric series, and today we're going to talk about some other types of series. So the next type of series that we're going to talk about is we're going to look at telescoping series. So geometric series and telescoping series are special, and the reason why they're special is because they're the two series that we can actually say what the sum of the series comes out to be. You're going to see as we go on, we're not going to be able to say what the sum of the series is. We're just going to be able to say whether or not the series converge or diverge. But for geometrics, I'm going to put a kind of little note up here. Geometric series and telescoping series are the two series we can find the sum. So you're going to see as we go on to the next section, we're not actually going to be finding the sum anymore. We're just going to be determining whether the series converges or it diverges. So telescoping series, so the hallmark of a telescoping series is that a telescoping series, the terms are going to be alternating between positive and negative. So the terms alternate between positive and negative. So usually, right, you have these pieces in a telescoping series where the reason it's kind of called telescoping is because pieces of it cancel each other out. So for example, I have the series n equals 1 to infinity of 2 over 4n squared minus 1. Now you might go, well, if I start plugging things in here, they're not alternating between positive and negative, right? If I put in a 1, I would end up with 2/3. If I put in a 2, right, I'm going to end up with 2/15. Those are not alternating terms, Dr. Gorman. So what are you talking about? And so the idea is that telescoping series, not every single one, but most of them actually come from being able to do partial fractions on a fraction, and then it turns it into a series where the terms are alternating positive, negative, positive, negative. So if we do partial fractions on this, so use partial fractions. And so we have here 2 over 4n squared minus 1. So remember, 4n squared minus 1, I could factor that into 2n minus 1 times 2n plus 1, because it's the difference of squares. And so that's going to end up being a over 2n plus 1 plus b over 2n minus 1. It doesn't matter what you put as the a and the b. I just put a over 2n plus 1 so that it lines up with what's in my notes, so that in case I make a mistake, I can look at my notes and know that I made some kind of mistake. Questions? Okay, so this is the same partial fractions we did before. So if we multiply this by 2n minus 1 times 2n plus 1, right, we're going to end up with 2 is a times 2n minus 1 plus b times 2n plus 1. And anybody want to take a guess? What's a nice value I could plug in here? Yeah, a half. So if n is equal to 1/2, we're going to have 2 is equal to a times 2 times 1/2 minus 1 plus b times 2 times 1/2 plus 1. So this first part here, this is going to 0. So we have 2 is equal to, the second one I have 2 times a half, which is 1, plus 1 is 2. So 2 is equal to 2b. So we end up with dividing both sides by 2. B ends up being equal to 1. And then I'll come on this side and find the other one. So what's another nice value I could plug in? Okay, minus 1/2. So I've got 2 is equal to a times 2 times minus 1/2 minus 1 plus b times 2 times minus 1/2 plus 1. So in this case, the second term here goes to 0, right? The first term I have minus 1, so that's a negative 2. So 2 equals minus 2a. Divide by negative 2. A ends up being equal to negative 1. And I don't want to run out of room, so I'm going to go to the next page, but I want to make sure, like, people are ready. So is there anyone that wants me to wait before we go to the next page? Yeah, I figured. Not a problem. Just let me know when we're ready. So basically, what we found is we had a fraction, and this is kind of telescoping series. You're either going to be given, when you're given this series, it's going to have 2 pieces to it, or it's going to be a partial fraction that you need to break apart to make it into 2 pieces. So we're going to have another type of series that alternates between positive and negative. It's actually called the alternating series, and that one's a little bit easier. That one is literally just when I plug in like 1, I get a, maybe a positive term. I plug in 2, I get a negative. Telescoping series are slightly different. Okay. So we started, kind of to sum up what we did. So we started with n equals 1 to infinity of 2 over 4n squared minus 1. And then we used partial fractions to split up that fraction. And so now we have n equals 1 to infinity. So our a was a negative 1. So we have the summation of negative 1 over 2n plus 1 plus 1 over 2n minus 1. Okay. So if I begin to kind of write out, let's begin to write out what this series looks like. If I begin to write out some of the terms. So if I put in n equals 1, right, I would have negative 1 over, if I plug in 1 here, I have 2 times 1 plus 1, right? So we have negative 1 over 3. Plus, if I plug in 1, I have 1 over, so we have 2n minus 1, so 2 times 1 is 2, minus 1 is 1. So this is the n equals 1 term. Plus, if I plug in n equals 2, I'm going to have negative 1 over, so 2 times 2 is 4, plus 1 is 5. Plus, if I plug in 2 into the second one here, we're going to have 2 times 2 is 4, minus 1 is 3, so plus 1/3. This is the n equals 2 term. And we'll do one more here. So plus, if we do n equals 3, if I plug in 3, I get negative 1 over 6 plus 1 is 7. Plus 1 over 2 times 3 is 6 minus 1 is 5. Plus, and we keep going, right? So if you look at the terms that are happening right now, Do you see anything kind of related between the pieces? Like, could I do anything else to this? Like if I was thinking about simplifying this. Okay, yeah. What about, does anything cancel out? Like, if you look at all the terms I have up there right now, is anything canceling out?
The first term of the thing in the parentheses before it is the opposite in the one preceding it as the second fraction.
Yeah. Yeah, exactly. So notice I have a negative 1/3, but then that shows up in the next term as a positive 1/3, right? I have a negative 1/5, but that shows up in the next term as a positive 1/5. And I could keep doing this, right? So if I wrote out even more terms, stuff would keep canceling, right? So the things that don't cancel out here are the 1 plus eventually, since this goes on forever, kind of everything else sort of cancels out. And I say sort of cancels out because if you're talking about true infinite, it goes on forever, right? So there's never really an end. So telescoping series is another one where we can look at what the partial sum is. So we can use the partial sum for telescoping series. So what we're going to write down is we're going to write down the s sub nth sum, right? So we're going to go out to the nth term. So what that is, what that is going to look like here is, so I had that negative 1/3 plus 1/1 plus, we had negative 1/5 plus 1/3 plus negative 1/7 plus 1/5. And if I even did one more here, so we did n equals 4, we'd have negative 1/9 plus 1/7 plus, eventually we'd get up to negative 1/2n plus 1 plus 1/2n minus 1. Right? So this is that nth partial sum. And then just like we said, the first piece is what's canceling out, right? This first piece, this negative 1/3, cancels this 1/3 here. This negative 1/5 cancels the 1/5 here. This negative 1/7 cancels the 1/7 here. This negative 1/9 would get canceled out with something in here, right? So if you notice, the positive 1 is canceling out the thing before it. So if I kept going, eventually this positive piece would be canceled out and we'd just be left with that end piece. So the nth partial sum ends up being 1 minus 1/2n plus 1. Questions? So this is why they're called telescoping, because it's like each piece has two pieces. One is positive, one is negative, and they end up canceling out as you're going down the line. So you're kind of that's what they mean by telescoping. These things are canceling out as they go down the line. And so if I look at the partial sum will help me figure out what's happening to the total sum. Questions? No. Okay, so now to find the total sum. So the sum is going to be equal to the limit as n approaches infinity. So as I let my terms go towards infinity, of 1 minus 1/2n plus 1. And if I plug in there, I end up with 1 minus 1 over infinity. right? And remember, 1 over infinity is 0. So I end up with 1 minus 0 or just 1. Right? In this case, my pieces don't blow up. It's possible, like, the pieces could have blown up and their sum would have went off to infinity, in which case we would have said it diverges, but here it's going to converge to this number 1. Questions? No. So the geometric series and the telescoping series are like special series. Okay. Geometric series shows up a fair amount. Telescoping series, not that much. They, like I said at the beginning, they're the only 2 series that we can find the sum for. So the remainder of what we're going to do, right? And that sheet, I have that sheet on Canvas for you guys. All the rest of them, if you look at that sheet, the rest of them don't show you any, they don't show you any terms, right? Let me pull that back up so you can see what I mean, they don't tell you any sums. So pull this up here. Okay, and I'll come back to this here, where I'm writing here in a second. But if you look, right, on these here, right, these tests, you'll notice that the only ones, right, that the only ones that show a sum, right, are here, are here under the geometric series and the telescoping series, right? None of the other series show a sum, right? So that's it. So these are the 2 series that we can use to find a sum. Everything else, we're just worried about whether things converge or diverge. And you might be curious, like, okay, well, if I can't find the sum, what good are these used for? So, series, here's kind of what series are used for. So they're used for a couple different things. Series are used for, so one of the things series are used for is they work in the background. Okay, so then the rest of the day we're going to look at, hopefully get through 3 tests. So we're going to get through the divergence test, we're going to get through the integral test, and the p-series test. So the divergence test. So if you noticed, right, as we were going through each of these, the geometric series and the p series, or not the p series, the geometric series and the telescoping series, right? Essentially, if you think about it, if I'm taking a series, right? So if we take a series, and actually I should. So summation n equals 1 to infinity of a sub n, right? If I'm not on my game here today. I'm just gonna point that out. Like, I know I'm not on my game. I got my 2nd dose of the vaccine yesterday, so my head kind of hurts and I'm kind of achy and stuff. So I'm just putting that out there if you're kind of like, wow, Dr. Gorman's a little all over the place today. It's true, I am. But that's why. So I'll be better next week. But we're gonna muddle through this together here today. Okay, so I have a series, right? Remember what's happening. Oh, thanks. Yeah. Remember what's happening with the series. We're adding all these terms, right? So we've got like a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot, 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 dot. Yeah, needles aren't the best, but it's better than getting coronavirus, right? That's my husband and I don't mind needles so much, but my husband really, really doesn't. But he's like, basically, he's like, it's better than, getting corona. So, we were pretty ecstatic when we got our first dose a month ago. So, but yeah, the second dose hits you a little bit harder than the first dose for anyone, if you want to know how that experience goes. Yeah, I have too. So we have A1 plus A2 plus A3 plus A4 plus such and such, right? So if these terms, right, if you look at the limit, so if we look at the limit as n approaches infinity of a sub n, and we're interested whether this sum, so remember, we're looking at whether the sum converges to a number or it diverges. And when it diverges, it tends to just blow up positively or negatively. It gets really, really super huge positive or really, really super huge negative. These terms need to be going to 0 to be able to have even a chance for the series to converge. Because let's say the limit of the terms went to 1. All of a sudden now I'm adding something that's plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. And if I keep adding an infinite number of plus 1s, that's going to go towards infinity. So if you look at this limit has to be equal to 0 for our series to have a chance at converging. So you can't, so basically that's kind of like a general fact, right? If we think about it as these terms go towards 0, if the terms are going towards 0, then at least I have a chance, right? As I'm getting out really far, as n's going to infinity, it's like I'm adding nothing to the series. So that's at least a chance for it to converge. It does not mean it converges. And so this basic fact here is what is behind our first major test that we look at, which is called the divergence test. Some places call it the nth term divergence test. That's technically the name of it. Nth term test for divergence. We're just gonna refer to it as the divergence test. Okay, so what the divergence test says is if the limit as n approaches infinity of a sub n is not equal to 0, then the summation n equals 1 to infinity of a sub n, so that series diverges. So the divergence test is kind of the easiest of the tests to apply, right? You can just quickly apply it, be like, is it working? Like does it happen? I can take a limit real quick. If the limit's not 0, I know it diverges and I'm done. If the limit does come out to 0, you cannot say it converges, and basically you have to try another test. So that's why we have a whole sheet of tests to look at. So, couple notes. The first one is what I just said. The divergence test cannot say that a series converges. Okay, so you cannot say that the series converges if you're talking about the divergence test. Secondly, if the limit doesn't exist, then the series also diverges, right? So I kind of put that out there specifically, right? Because when I say the limit as n approaches infinity of a sub n is not equal to 0, people think we're talking only about a number. But we're talking about if that limit turns out to be infinity. If you find that that limit doesn't exist at all, like you can't even find that limit, then you can also say that the series diverges. Questions? And I'm going to say that the hardest thing about series, right? Like the hardest thing about series is trying to figure out what test to use on series, right? So when we do the homework for these sections, what will actually end up happening is as we get more series as we get more tests, I should say, throughout the sections, the homework still might have a geometric series on it. It still might have a telescoping series on it. So basically, the further along we go in the chapter, the homeworks that I'm making still make you try to figure out, okay, what can I use? So it's not like the homework from section 11.2, you just are going to use the divergence test on, right? Or in section 11.3, we're going to learn about the integral test. So it's not like all the problems in the integral tests in section 11.3 are just going to use the integral test. So just kind of to put that out there. Okay, so let's try some of these. So use the divergence test. Oh, yep, I totally can go back. No problem. Anybody else need me to wait? No. Okay. Use the divergence test to determine if the series diverges, right? Now, in the future, right, like I said, we're just going to be given, like, when it's time for the test on all of this stuff, you're just going to be given a, blanket thing that says, determine whether each of the following series converges or diverges. Okay. So it's not enough to be like, well, it doesn't I don't know if it diverges. But here with the divergence test, we're going to have an answer. It's kind of like, I don't know, maybe. All right. So A, the series n equals 1 to infinity of n squared. So if you look, we're adding 1 plus, 2 squared is 4, 3 squared is 9, 4 squared is 16. So we're adding all those things, right? Now, if you think about it, it kind of would make sense that that's not going to converge because I'm going to keep adding bigger and bigger and bigger numbers. But it's not enough to just be like, oh, I think that's not going to work, right? We have to actually show it. So you want to be clear about what test you're using. So we're going to try using the divergence test. So we're going to look at the limit as n approaches infinity of n squared. And so what is that limit? Limit as n approaches infinity of n squared. Yeah, so I mean, I'm not going to mark you off if on the homework you don't write what test you're doing, but when it comes time for the test on the series tests, you want to write what test you're doing, because then I will take off. So it's a good habit to just get into as you're doing the homework, to write down what test you're using. And you're going to see me model that for you guys too. I'm going to write down the test, and then some of the tests have conditions that have to be met to be able to use the test. So you'll see, I'll write those down as well. And then, yeah, so Sandra said that the limit as n approaches infinity of n squared is infinity, and infinity is not equal to 0. So the series diverges. So B, summation n equals 1 to infinity of the natural log of n over 3n. So again, I'm going to use the divergence test. So we're going to look at the limit as n approaches infinity of the natural log of n over 3n. And so if I plug in infinity, what happens here? Yeah, you end up with infinity over infinity. Okay, so what do I have to do if I have a limit that's infinity over infinity? Yeah, I have to do L'Hopital's rule. So that's what I'm going to do. So I'm going to take the derivative of the top. So we're looking at the limit as n approaches infinity. So the derivative of the top, the natural log of n, is what? Yep, 1 over n. And on the bottom, we just have 3. So we're really looking at the limit as n approaches infinity of 1 over 3n. And so what happens to that limit? Yeah, so if I plug in here, right, I end up with 1 over infinity. And you can, right, you do not need to write this part out. If you want to kind of jog your memory that, oh, this is 1 over infinity, you could write it as 1 over infinity. But this whole thing is equal to 0, right? So remember, the divergence test only tells us stuff if the series is not equal to 0. So here, basically the divergence test doesn't give us any information, right? So we're kind of like out of luck. So tough luck. I don't know if it diverges. I don't know if it converges. I can't tell, right? So a couple sections from now, like after Tuesday's class, if you got a problem like this, then we would keep going and we'd be able to figure out what happens to it. For right now, that's the best we can do, right? So for right now, all we can say is, I don't know what happens. We need more information, right? So stay tuned. Stay tuned for more tests. I still have a couple more examples to do here, but questions? No. Can I go on to the next page? Yes. Okay. All right, so C, summation n equals 1 to infinity of n plus 1 over n. So n plus 1 over n, so again, if I'm using the divergence test, we're looking at the limit as n approaches infinity of n plus 1 over n. And so what happens to that as I plug in? Yeah, infinity over infinity. So if we do L'Hopital's rule again, we get the limit as n approaches infinity. The derivative of the top would be 1. Derivative of the bottom is 1. So our whole entire limit is 1. So the limit turns out to be 1. 1 is not equal to 0, so it diverges. And I have one more of these. So the divergence test is pretty nice. It's like the easy test to apply. It's like quick, right? The problem with it is it just doesn't work all the time, as we saw in the last example. So summation n equals 1 to infinity of negative 1 to the n. So if you think about what's happening to negative 1 to the n, right, you're just bouncing back and forth between positive 1, negative 1, positive 1, negative 1, positive 1, negative 1, right? Or I guess technically you're starting at negative. Negative 1, positive 1, negative 1, positive 1, back and forth, back and forth. And this is not, it kind of looks a little bit like a geometric series, but remember in a geometric series, the absolute value of r has to be bigger than 1 or less than 1. We don't talk about what happens at 1. And this is why. And so if I do the divergence test, and we look at the limit as n approaches infinity of negative 1 to the n, the problem here is I can't say what this limit is, because as n gets really big, it still just bounces back and forth between negative 1, positive 1, negative 1, positive 1, negative 1, positive 1, right? It doesn't actually settle down to anything in particular. So this limit does not exist. Like, we can't find what this limit is. Right? So it doesn't exist because it bounces back and forth between positive 1 and negative 1. Okay, so limit doesn't exist, diverges. Right? So for it to converge, the limit has to get 0. So whenever we get an oscillation like that, we consider it to be indeterminate. No. It's so the short answer is no. The problem is this one's very clear, right? It's bouncing back and forth between positive 1, negative 1, right? So like if you think about if you were drawing a picture, right? It's bouncing like back and forth this way, right? The exact same amount. You could have something oscillate back and forth, but it could look more like this. And every time I jump, I get like a little closer to 0, right? So even though I'm going back and forth, I'm technically getting closer and closer to 0. So that is a different scenario. That's why there will actually be an alternating series test. So one that you use if stuff is bouncing back and forth and it's not just a strict number bouncing back and forth. Does that answer your question, Sandra? Yeah. So it's, basically if it's oscillating, if it's staying the exact same thing and it's not changing, it's just bouncing back and forth between two numbers, then the limit's not going to exist and it's going to diverge. Yeah, the second picture does look a little bit like Gabriel's horn. So it is actually kind of, it's called the harmonic function, or the alternating harmonic series. And so it bounces back and forth, kind of like 1 over x, basically. No problem. Other questions? No? Okay. So then, anybody need me to wait before I go to the next page? Sure, not a problem. Okay. All right, so let's do that harmonic, let's do that harmonic series. So let's look at the summation n equals 1 to infinity of 1 over n. Okay, so we already talked about how we couldn't do the other tests, right? So we're going to try the integral test. And so we're going to let f of n be equal to 1 over n. And so I want to know, first off, are these things positive? So as I begin to put in values in for n, is 1 over n positive? Yeah, right? You might go, well, it's negative if you put in a negative value. We're not worrying about putting in negative values, right? And the reason we're not worrying about that is because our n is starting at 1. So if you're starting at numbers 1 and bigger, when I plug them in here, this is definitely going to be positive. Okay. 2, we want to think about if it's continuous, right? Now, you might go, well, 1 over n, that's really the function 1 over x, right? And 1 over x looks like this. And you go, that's not continuous. What are we doing? Remember, we only care about from where we start. So we're starting at 1, right? So everything we're talking about starts here at 1 and goes this way. So if I'm starting at 1 and I'm going to the right there, is my function continuous from that blue line over? Yeah. So it's positive, it's continuous, right? And then the last thing I have to do is I want to check if it's decreasing. Okay, so the easiest way to check if it's decreasing is to compare the one term with the next term. So if I have 1 over n, right, and you could look here in the picture, right, it's a decreasing function. So you could graph it. You could graph it and say, yeah, it's decreasing. I checked the graph. If you're not going to check a graph by hand or by punching it in and looking at it, the way to determine if it's decreasing is by answering the question is 1 over n, is that actually bigger than 1 over n plus 1? So if you think about it, right, the first one between the left side and the right side, the denominator is getting bigger. So 1 over n plus 1 is going to be smaller. The other thing you can do, right, but you have to be careful that you do it the correct way. But you could technically cross multiply. But when you cross multiply, you have to do this direction first. So we're basically asking, is 1 times n plus 1, is that bigger than n times 1? So is n plus 1 bigger than n? Yeah. And so sometimes this cross multiplication thing will actually help you figure it out faster. At least for me, it's faster than graphing it. So I am in fact decreasing, right? So I'm positive, I'm continuous, I'm decreasing. And for functions that are kind of obvious, right? So like 1 over n here, it's obvious it's positive. We all know it's kind of like 1 over x, and that is a decreasing function and that it's continuous. As long as you state like positive check, continuous check, decreasing check, so I know that it is always good to be positive in life. So that I know that you did remember I do have to check these things, then I'm fine with that, right? So you don't have to show a lot of work for checking it's positive, continuous, and decreasing, but you have to show me that you knew you had to check it. Okay, so now we're going to be looking at the integral from our number here started at 1. So we're going to be looking at the integral from 1 to infinity. And then we generally use an x instead of an n. If you want to do 1 over n and dn, that's fine. But we generally do 1 over x dx. And so here's where I will allow you to get a little loosey-goosey. If you don't formally rewrite this as a limit, like I'm kind of okay with it. Because theoretically you showed me you knew how to do that. But really what's going on, oops, not n, is we're looking at the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. And what is the integral of 1 over x? Yeah, natural log of the absolute value of x. So we're looking at the limit as b approaches infinity of the natural log of the absolute value of x evaluated from 1 to b. Again, R1 to b is all positive, so if you drop the absolute value here, that's okay. But we're looking at the limit as b approaches infinity of the natural log of b minus the natural log of 1. Natural log of 1 we know goes to 0. So what is that limit going to be as b goes to infinity? What happens to the natural log of b? Yeah, it also goes to infinity. And so then this diverges, right? When we get our integral is an infinite, either positive infinity or negative infinity, it's saying our integral diverges. And then therefore, the summation n equals 1 to infinity of 1 over n diverges. And mathematically, like you might see me write this more in, because we write therefore a lot in these problems. There is a mathematical symbol for therefore. It's 3 little dots. So those 3 little dots are the mathematical symbol for therefore. Questions? Yeah, they're kind of sort of like proofs. They're not exactly proofs, but they're more like a proof than like a calculate something problem. Other questions? Should we try another one? You're all like, sure, why not? Maybe. But we'll do another one. Does anybody need me to wait to go to the next page? No? Okay. So here's another one. So the summation n equals 1 to infinity of e to the negative n. Okay. So if I think about this, this is really the summation n equals 1 to infinity of 1 over e to the n. On my paper, I did this as a integral test. You don't really have to use the integral test. You can. It will work out for the integral test, but what other kind of function, what tests could I maybe use this for? Yeah, it's really a geometric series, right? So why go through all the work of the integral test if it actually looks like a geometric series? So I would just use the geometric series. So this is a geometric series, right? In our case, r is equal to 1 over e. So if we look at the absolute value of r, that's just going to be 1 over e. So how does 1 over e compare? Is it less than 1 or bigger than 1? Yeah, it's less than 1. And what did the geometric series say if your r is less than 1? Yeah, it converges. Okay. I will have another integral test to show. Yeah, so in this case, in terms of the geometric series, your A would be a 1. Yep. And this didn't ask us to find the sum, but if it did, it would be, right, this is one of the ones we can find the sum. So the sum is going to be, remember, I said it's the first term divided by 1 minus r. So in our case, the first term is going to be 1 over e, plug in that n value, that first n value, so 1 over e to the first, divided by 1 minus 1 over e. So we'd have 1 over e divided by 1 minus 1 over e. I'd probably multiply top and bottom by e to make stuff nicer. So we'd have 1 over e minus 1. So that's what the sum would be. So I don't really worry too much about what the A is. You need to worry about what the A is if you want to use the formula, like the other formula for the sum. But then you also have to worry that your summation is in the right like configuration. And so I don't like to worry about the right configuration. So as soon as I know it's a geometric series, I just know that the sum is always going to be the first term, whatever that is, divided by 1 minus r. Does that make sense? Other questions? So that was a nice little surprise. Easy problem, right? So the next thing we're going to do is we're actually going to look at kind of a class of problems. So let me stop. Okay, so we're going to look at what about the summation n equals 1 to infinity of 1 over n to the p, right? So this is different than the geometric series. In the geometric series, the n is the exponent, right? Here, the n is the base, not the exponent. So the exponent is some actual number, right? Where p is some number, right? So p could be 5, p could be, -3, p could be 17. So p is some actual number, right? So a lot of people confuse, like, wait a minute, isn't that just a geometric series? No, it's not, because the n is not the exponent. Okay, so this is a candidate for the integral test, right? So we're going to try to do the integral test on this. This is not a problem that I would, like, give to you and expect you to do with the p in it. We are going to actually use this to create what is called the P-series test. So we're basically developing a test, so I'm showing you where the P-series test comes from. So you don't have to be able to reproduce what I'm going to do right here, right? You have to be able to do the integral test like we did on the 1 over n, but you don't have to be able to do this. So here, so we're going to try to use the integral test. So we're going to let f of n be equal to 1 over n to the p. And so our n, right, we're putting in numbers 1 and higher. So the numbers we're sticking in are positive. So this is definitely going to be positive. It's continuous. So again, once, the only place where it's bad is when n is 0, and n equals 0 doesn't happen in our summation, so it's continuous. And then we have to check decreasing. So we're looking at comparing, is 1 over n to the p, is that greater than 1 over n plus 1 to the p? And yeah, right, the denominator of n to the p is smaller than the denominator of n plus 1 to the p. So when I divide by it, right, when I'm on this side, I'm dividing by a bigger number, so the total number here is smaller. So yes, so it's continuous, it's positive, it's decreasing. So we're going to then look at the integral from 1 to infinity of 1 over x to the p dx. And so that's going to be the limit as b approaches infinity of the integral from 1 to b of, I'm just going to rewrite this as x to the minus p, just to make it easier to integrate, right? So again, it's a little weird. We're dealing with not an actual, I'm not dealing with 1 over x cubed, but in essence, that's kind of what we have, right? So remember, p is just some number. So how do you integrate x to a power? What do you do to integrate that? Like, if I was integrating x to the 7th, right, what would you do to integrate that? Yeah, you add 1 to the power and then divide by that number. So we're going to do the same thing here, right? So this is going to be the limit as b approaches infinity of x to the minus p plus 1 divided by minus p plus 1, evaluated from 1 to b. Now, first off, since I divided by negative p plus 1, I have to be careful, and I have to say right now, p better not be equal to 1, right? If p is equal to 1, I'm in trouble, because now if p is equal to 1, that denominator is 0, right? And if p is equal to 1, we're talking about just 1 over n. And we already looked at what happened to 1 over n, right? So, kind of put here, side note, if p equals 1, we have the summation n equals 1 to infinity of 1 over n, which was the harmonic series. And we said that diverges. Right? So we do know what happens if p equals 1, so we don't have to actually worry about that. We did that earlier. Okay, so if I plug in, I get the limit as b approaches infinity, b to the minus p plus 1 over minus p plus 1 minus 1 to the minus p plus 1 over minus p plus 1. And now you go, okay, that's great. But now I don't know what p really is. So how am I supposed to figure this out? So the answer is, yeah, I don't know what p is. I know that p is either a number bigger than 1, though, or I know it's a number less than 1. Right? So basically, we're going to have two things come out of here. If p is bigger than 1, or if p is less than 1. Right, so if p is some number bigger than 1, one thing's going to happen. And if p is some number less than 1, another thing's going to happen. So let's think about if p is bigger than 1. So if p is bigger than 1, so say p is like 10, right? If I were to plug 10 in here, I'd have b to a negative power, right? Because negative 10 plus 1 would give me negative 9. So I would have infinity, like when I plug in infinity, I'd have infinity to a negative power, right? And remember, infinity to a negative power, like infinity to the negative 9th, is going to be 1 over infinity to the 9th. So if you're in this first case, when p is bigger than 1, what's happening is b to the minus p plus 1 approaches 0. And so in this case, you're going to converge. And if p is less than 1, so say p is negative 10, when you plug in negative 10 into here, you would have negative 10. So you'd end up with like 11. So b to the 11th, that's b to a positive number. And now you're going to have infinity to a positive number. So in this case, b to the minus p plus 1 is going to go towards infinity. And so in this case, it's going to diverge. So because that P, I didn't know the exact value of P, I can't exactly say what happens, but I kind of have rules now. So if P is bigger than 1, it's going to converge. If P is less than 1, it diverges. And I already knew if P was equal to 1, it diverged as well. So I can sum all of that up with the P-series test, which is essentially what we just derived there. So we use the integral test to actually come up with this new test called the P-series test. So I figure people probably need me to wait a minute before I go to the next page, but then I'll summarize the P-series test and we'll do a couple P-series examples. So geometric series, P-series, they're both actually pretty nice, easy series to figure out what's happening. Does anybody need me to still wait a minute before I go to the next page? Okay. Okay, so the P-series test. So the P-series test, you have the summation n equals 1 to infinity of 1 over n to the P. And if P is greater than 1, it will converge. And if P is less than or equal to 1, it diverges. So, for example, determine the following converge or diverge. So A, the summation n equals 1 to infinity of 4 over n to the 7th. So, even though there's a 4 there, that doesn't actually change the fact that it's a P-series. So I know in the P-series test I wrote it as a 1, but you can, that 4 is just a constant, and so you could actually factor that 4 out in front of the summation. So this is still really 4 times the summation n equals 1 to infinity of 1 over n to the 7th. So that's a P-series, right? And in this case, P is equal to what? 7, and 7 is bigger than 1, so it converges. Yeah, it is pretty easy. The only thing you have to watch out for is sometimes they don't look exactly like a P-series. So, for instance, you could have the summation n equals 1 to infinity of the square root of n over n. Right? And you might look at that and go, that doesn't look like a P-series. But I could rewrite it, right? So, square root of n is n to the 1/2 power divided by n, or summation n equals 1 to infinity of 1 over n to the 1/2. So now it looks like a P-series. Okay? And what's my P? Yeah, 1/2. Is 1/2 bigger than 1 or less than or equal to 1? Yeah, it's less than or equal to 1, so it diverges. Right, so if you happen to have, a couple different things happening with n, and they're multiplied or they're divided, it's probably a p-series, and you just kind of have to rearrange the terms a little bit. But otherwise, yeah, p-series are pretty nice. Questions? No. I don't know what I don't know. Yeah, so that's kind of part of the problem with series, right? So series is the first topic in Calc 2, or in calculus, or probably even in your math kind of career, where it's no longer just cookie cutter, right? It's no longer just like, oh, see this, do this, or see this, do this, right? Now it's kind of like I have to figure out what I'm applying and then do that. And so there's not cut and dry ways of doing that. And so the idea is the most valuable thing is just to see examples and to hopefully see how people work through examples. So that is all the tests we're going to learn for today. So what I have left for us to do is 1, 2, 3, 4. So I have 4 different examples, so that you can see me work through those 4 different examples, and they encompass potentially all the different tests that we've done. Okay, so you can see my thought process, like I'm going to talk out loud how I approach a problem. And so that way you can kind of be like, oh, okay, maybe this is how I should approach this problem. And right now it's easier, right? So this is why I kind of said at the beginning of class, even though the section 11, like we are going to finish 11.3, and even though the 11.3 homework is not due until April 5th, and I'm not going to go change that, it really is in your best interest, though, to do it, if you can do it before next class, to do it before next class, because we're just going to keep adding more tests on, right? So it's easier to kind of learn the tests when there's less tests, then once we get further along and there's even more tests to learn, then it gets even like harder to figure them out. Try some where it's all mixed up. So determine if the following converge or diverge. So A, summation n equals 1 to infinity of 5 over n plus 1. Okay, so I look at this, and the first thing I do in my head when I'm doing series is I first try to figure out, is it geometric or is it p-series? Because those are like very concrete, right? They have to look a certain way. So if I look at this, it's not geometric because I don't have stuff raised to the nth power, and it's not a p-series because I don't just have like 5 over n. If I just had 5 over n, it could be a p-series, but I have 5 over n plus 1. So this is not just, this is not either one of those. So then I try to figure out, do I think the divergence test is going to work? So I've been doing this long enough that I can look at a problem and go, the limit of that is going to be this as we approach infinity, so nope, divergence test isn't going to work. You might not be able to do that yet. So the first thing you might say is you might go, okay, I can see it's not a geometric series. I can see it's not a p-series. And you might try the divergence test. And if I tried the divergence test, we'd be taking the limit as n approaches infinity of 5 over n plus 1. Okay, so what is that limit? Yeah, 0. Tough luck. Okay, so not geometric, not p-series, divergence test didn't help me out. It's not a telescoping series because there's no way for me to break that down even more, right? I can't take 5 over n plus 1 and break it down into 2 like smaller fractions because there's nothing for me to factor in the bottom there. So the only thing I'm left with then is the integral test. So all right, we'll try the integral test. So for the integral test, we're going to let f of n be equal to 5 over n plus 1. And so remember, we have to check, is it positive? And so, yeah, right? As I begin to put in values of n that are 1 or bigger, it's going to be positive. Is it continuous? Yep. Again, it's continuous because the only place that that function has a problem is when the denominator would be 0, and the denominator is 0 at -1, and -1 is not part of our sum, so it's continuous. And then the third thing we have to check is if it's decreasing. Right? So again, we're looking at 5 over n plus 1. Is that bigger than 5 over... So instead of n, we replace n with n plus 1 over 1. Or n plus 1 plus 1. So we're basically want to know, is 5 over n plus 1, is that bigger than 5 over n plus 2? Yeah. Should have put my little question mark here. Excuse me. So I'm positive, I'm continuous, I'm decreasing. Right? So that's all good. So now we're going to look at the integral from 1 to infinity of 5 over x plus 1 dx, or the limit as b approaches infinity of the integral from 1 to b of 5 over x plus 1 dx. These should look kind of familiar from when we were doing the partial fractions section, right? So this is just the limit as b approaches infinity of 5 natural log absolute value x plus 1 evaluated from 1 to b. So we're talking about the limit as b approaches infinity of 5 natural log b plus 1 minus 5 natural log of, 1 plus 1. And so what happens to the natural log of b plus 1 as b goes towards infinity? Yeah, it goes to infinity. So this is equal to infinity. So it diverges. So our series, push this up a little bit, summation n equals 1 to infinity of 5 over n plus 1 diverges. Right? Our integral diverged, which means our series also diverges. Questions? So again, right? So I try to, when I'm doing these problems, I try to look and go, hey, does it happen to be a p-series? Does it happen to be a geometric, or does it happen to be a p-series? Does it happen to be a geometric series? If it's one of those, I take care of that. If it's not, then I move on and I go, okay, well, could I use the divergence test on it? I try that. And then I try to do some of the harder things. I personally, I don't like the integral test that much. You're going to find out as we go on and we learn some more high-powered tests that a lot of tests you could use the integral test on, you could actually use something else on. And so you can usually use, not all the time, right? But a lot of times you could use what's called the comparison test or the limit comparison test. And so to me, those are faster. And so I tend to do those. So I tend to only use the integral test when I absolutely have to. But right now, it's the next best thing we got. So we're going to have to use it a couple times, potentially. All right. So let's try a couple more here. So B summation n equals 1 to the to infinity of 1 over the natural log of 3 to the n. All right, so yeah, this is a geometric. So as soon as you see n in the as a power, especially if that's only showing up the one time and nothing else is going on like it is here, then that's an indication that this is probably a geometric series. So if we look at this, I have n equals 1 to infinity. I could think of this is really 1 over the natural log of 3, all raised to the nth power. So this is geometric. And our r is 1 over the natural log of 3. And so the absolute value of r is the absolute value of 1 over the natural log of 3. And is that bigger than 1 or less than 1? Yeah, it's less than 1. And what happens in the geometric series if you're less than 1? Yeah, converges. I should also say, right, especially because we're in this online, web remote, whatever environment. So that sheet that I have up that has all the tests, right? I think I said this last time, but I will let you have that on the next test, right? So if you want to print it off before the test, you can. I'll have it in the test file as well. So you don't have to memorize the tests, right? It's really more about can you figure out what test to apply and do the steps of the tests correctly. Okay. Questions? No. All right. So what about the summation n equals 1 to infinity of negative 2 over n squared times the cube root of n? Okay, so again, I kind of look at it and I go, okay, well, do I think it could be a geometric series or a p-series? It's not a geometric series because my n is not a power, right? So for the geometric series, if you notice, right, the n has to be as a power. But as a p-series, do I think I could rewrite this so that it was a p-series? Yeah, so this is going to be the summation n equals 1 to infinity, negative 2 over n squared n to the 1/3. Right? Remember the cube root of n is n to the 1/3. So this is going to be the summation n equals 1 to infinity of negative 2 over, so I have 2 plus 1/3, right? So if I take 2 plus 1/3, 2 is 6/3, right? So 6/3 plus 1/3 is 7/3. So n to the 7/3. So this is a p-series. Our p is 7/3. And how does 7/3 compare? Is it bigger than 1 or less than 1? Yeah, it's bigger than 1. And what did we say? Does that mean the p-series converges or diverges? Okay, so yeah, you gotta be a little careful, right? The p-series and the geometric series are like flip-flopped of each other, right? So in the geometric series, so remember in the geometric series, if the absolute value of r is less than 1, it converges. And if it's greater than 1, it diverges, right? But in the p-series, if p is greater than 1, then it converges. And if p is less than 1, then it diverges. Right? So the two series are kind of flip-flopped from each other. So this one is greater than 1, so this one is actually also going to converge. That's it. So you're just trying to determine whether the series converges or diverges. I lied. I have 2 more. So I think we can do them. I don't know if we can do both of them. We'll see. So we'll try this one first. Summation n equals 1 to infinity of 5 to the n over 4 to the n plus 3. So if you look at this, you might go, oh, it's got powers of n. That's kind of like a geometric series. And yes, if this plus 3 was not here, this is absolutely a geometric series. You could rewrite it as 5/4 all to the n power. So telescoping, remember telescoping, I'm going to want to be able to take this and break it into 2 pieces where things will add and subtract together. And so this is not, I can't break it, if it was on the top, I could break it into 2 fractions, but since the plus 3 is on the bottom, I can't break it into 2 fractions. So it's not a telescoping, it's not a geometric, it's not a p-series. So I'm going to try the divergence test. So try divergence test. So we're going to have the limit as n approaches infinity of 5 to the n over 4 to the n plus 3. And if I do this, right, if I plug in, I basically get infinity over infinity. So I have to do L'Hopital's rule. So we talked last class, right, about the derivative of a to the n. So what's the derivative of 5 to the n? Yeah, 5 to the n ln 5. And then similar fashion, the derivative of 4 to the n is going to be 4 to the n ln 4. And now you might go, gee, Dr. Gorman, you didn't really make that problem any better, right? Because I still have a 5 to the n. I still have 5 to the n and 4 to the n, so I still have infinity over infinity, and that part's never going to go away. And I'm going to tell you, I did make it better because I got rid of the plus 3, and the plus 3 is what's kind of causing us problems. I can now think of this as the limit as n approaches infinity of 5/4 all raised to the n power times the natural log of 5 over the natural log of 4. So I just kind of rewritten stuff there a little bit. Natural log of 5 divided by natural log of 4, that's just a number. But now I have 5/4 raised to the n power. And 5/4 is some number bigger than 1. So I have some number bigger than 1 that I'm raising to the infinite power. And so this whole thing is just going to turn out to be infinity. And infinity is not equal to 0, so it diverges, right? The divergence test just says, hey, find the limit. If the limit is not 0, then it diverges. Questions? No. Okay. I have 11 minutes. I think I can do my last example in 11 minutes. And it's a good example to see. So, does anybody need me to wait to go to the next page? Okay, so this is E. Summation n equals 1 to infinity of n over n squared plus 1. Okay, so again, if we looked at this, It's not geometric. It's not a p-series. If the bottom was n squared minus 1, then that would be a candidate for it to potentially be a telescoping series. But the bottom is not n squared minus 1. I can't factor it. It's n squared plus 1. So it just is what it is. So you could try the divergence test. I'm going to kind of save us divergence a little bit of work here. If you take the limit as n approaches infinity of n over n squared plus 1, it ends up being 0. So you're in that tough luck case. Right. And it's not a hard limit to do, right? You would just get infinity over infinity and then have to do L'Hopital's rule. But because I want to make sure I get through the whole problem, I'm not going to work that all out. So then we're left with the integral test, right? So we're going to try the integral test. So f of n is going to be n over n squared plus 1. So it is positive. Right? I keep putting in positive numbers. That's fine. It's continuous. The bottom is never equal to 0, right? Because I have n squared plus 1. So it's a continuous function. And then I want to know if it is decreasing. So this is one where you're kind of like, it's a little hard to just tell, right? So that's kind of why I want to show this problem. So we're comparing n over n squared plus 1. Is that bigger than, so I'm going to replace everywhere here in n with an n plus 1 over n plus 1 squared plus 1. And so this is not as easy to say, hey, yeah, it definitely is decreasing like we did in the other problems. The reason why is because while, yes, here I have a bottom, and this bottom is definitely bigger than this bottom, the problem is that this top is also bigger than this top. So does it actually balance out? So this is one of the ones where my multiplication trick is helpful. So if this is true, then you're saying n times n plus 1 squared plus 1. I want to know, is that bigger than n squared plus 1 times n plus 1? So if you work out the algebra for those, right? If you like square it and then multiply through with the n and FOIL the right hand side. Again, for time's sake, I'm just going to say what that ends up being. On this side, you have n cubed plus 2n squared plus n plus 1. And we want to know, is that bigger than n cubed plus n squared plus n plus 1? And now, yeah, you can say, and yes, can you plug it into Desmos and see that it's a decreasing function? Absolutely. So you could take n over n squared plus 1, stick it into Desmos, and say, yeah, I know it's a decreasing function. Yep. So either one of those works. Okay, so now I can actually do, yeah, go ahead, Robert. Okay, so because basically what I'm doing is I'm taking the original term and then I'm saying what the next term would be. So the next term would be if I bump up n by 1. So it would be n plus 1, and then in here it would be the quantity. This n here would get replaced with an n plus 1. So like, you know, if I put in 5, I put a 5 here and a 5 here. The next term would be if I put in 6. So I'd have a 6 here and a 6 here. So n got bumped up by 1, and this n got bumped up by 1 as well. Yeah, you could apply a limit to show it's decreasing too. Sure. So since the limit is approaching 0, you could say that, yes, it's decreasing as well. Yep. I'm okay with that too. As long as you somehow show me it's decreasing, I'm okay with lots of different ways. Okay, so now we have to just do the integral, right? So we're looking at the integral from 1 to infinity of x over x squared plus 1 dx. So we're talking about the limit as b approaches infinity of the integral from 1 to b of x over x squared plus 1 dx. So how am I going to integrate x over x squared plus 1 dx? Yeah, u sub. So I'm going to come over here on the side and do it. So if I have x over x squared plus 1 dx, right, u is going to be x squared plus 1. Du is going to be 2x dx. So I need a 2 in here and a 1/2 out here. So we're going to get 1/2 the integral of 1 over u du, or 1/2 the natural log absolute value of u, or 1/2 the natural log absolute value of x squared plus 1. So this is going to become the limit as b approaches infinity of 1/2 the natural log, the absolute value of x squared plus 1, evaluated from 1 to b, or the limit as b approaches infinity, 1/2 the natural log of b squared plus 1, minus 1/2 the natural log of 1 squared plus 1. And if I plug in that limit, that first piece there, the 1/2 natural log of the absolute value of b squared plus 1, that goes to infinity. So this whole limit is infinity, so it diverges, right? So our sequence ends up diverging. Questions? No. Okay. So then that's the end for today. We have more tests we're going to learn next week. By the end of next week, before spring break, we'll have learned the majority of all the tests. And then after spring break, we'll do some, more interesting stuff with series and sequences. There'll still probably, I think there's still a couple tests. One test we probably are going to do after spring break. I can't remember the schedule off the top of my head. But otherwise, I will see you guys all on Tuesday.